Hi, my name is Onno, and this is joint work with Michael Mühlebach and Claire Bernard on partially observable reinforcement learning with memory traces. So in many environments in reinforcement learning, we don't get full state observation. So this is a very simple example called the T-maze, where the first observation is red or green, and it tells us whether to go up or down at the end of the corridor. So if we walk through this environment as a simple reactive agent, then it would look something like this. So we start at the left, we get the first observation, in this case it is green. Then we walk until we reach this decision state. And now we have to make a decision based on just this blue observation, which doesn't tell us anything. So it's simple to make the wrong decision. So the takeaway here is that in many environments, it is necessary to have some kind of memory. And by memory, I mean a compressed representation of the history of observations. The most typical memory that is used in reinforcement learning is sometimes called frame stacking, and it's simply a sliding window of a fixed number of the most recent observations. So in this notation, y0 is the most recent observation. And in this paper, we analyze something a little different, which we call the memory trace. And this is simply an exponential moving average of all the observations. In this case, the observations are vectors, and we have a forgetting factor lambda. And just like the length m window, these memory traces can be easily recursively computed. So at each time step, you can take the old memory and the new observation and combine them to get the new memory. Now, why would this be a good approach? Let's look again at the T-maze. So again, we start at the left with an empty memory trace, and then we get our first observation, and according to the formula, we just add it to our previous memory. We get the next observation, we scale down the previous memory, and we add the new observation, and we go on like this until we reach the decision state. And in this case, we can see that this information from the very beginning is still visible in the memory trace, which we can use to make the right decision. Now, concretely in this work, we consider the problem of policy evaluation with offline data. So the environment is a hidden Markov model, and the observation space is assumed to be one hot. And the question we ask is, how much data do we need to accurately estimate the value function? Now, because this is a partially observed setting, the value function is a function of the complete history of observations, and we want to minimize the return error. So given a function class, we want to find the function f in this function class that minimizes this quantity. And for Windows, this function class is given by first a truncation. So we truncate the complete history to give us the length m window, and then we apply an arbitrary function to this length m window to map it to the real numbers. So for memory traces, we can do a very similar thing. So we first map the history of observations to the traced space using the exponentially weighted average, and then we map this memory trace to a value in the real numbers. Now, to understand how memory traces with a forgetting factor lambda compare to window memories, we need to look at this set of possible memory traces, Z lambda. And to understand this, I've illustrated it here in a very simple setup. So there's only 3 possible observations. These are one hot, so they are the canonical basis vectors of the 3-dimensional space. And by the construction of memory traces, that means that also all memory traces are linear combinations of these 3 vectors. So they are in this 3-dimensional space. However, to visualize it, I've projected it down onto 2 dimensions here. Now, if we have 0 observations, then the memory trace is simply the empty sum, so we're at 0. If we get a single observation, so a length 1 history, then the memory trace is just a scaled version of that observation vector. If we have a length 2 history, then the memory trace is constructed by adding to this most recent observation the previous one but scaled down. So concretely, for example, in this triangle up here, all memory traces end with the observation A. This is because the most recent observation kind of is more dominant and tells you where in the space you are. If we add another observation, then the very similar thing happens. So now let's look at all the all the memory traces in this triangle. They all end in the letters BA. So those are the two most recent observations. And we can go on and on like this, and we can add longer and longer histories until we get this kind of picture that emerges. Now this picture is only valid for a lambda of 1/2. And if we change lambda, then we can see that the picture changes. So for small lambda, all these triangles get very small and separated from each other. But for large lambda the memory traces all flow together and overlap. Now what we can see from this picture is that if lambda is less than 1/2, so all these triangles are well separated, then any two distinct histories will always be mapped to two distinct memory traces. So, for example, if one history has the most recent observation A and the other has the most recent observation B, then clearly in this picture, one memory trace will be in this triangle and the other one will be in this triangle. So those two memory traces can't overlap. And more generally, if two histories differ in an observation that is several time steps ago, then they will also belong to two different triangles. And this we can see by zooming into this picture. Because of the recursive structure of how this space is defined, that means that all memory traces corresponding to histories that share a certain length of observations, most recent observations, they will always lie in a triangle like this. So in this case, if the the observation 6 time steps ago is different, then they will lie in two different triangles when you zoom in. So what does this have to do with learning value functions? How can this tell us whether it is more efficient to learn with memory traces or with sliding windows? So to understand this, we look at statistical learning theory, which tells us that it is more easy to learn a good value function if the size of the function class that we consider is small. And in this case, we consider the size measure, that is the metric entropy of a function class. Now for windows of length m, we can compute this metric entropy, and we can see that it scales exponentially in the window length m. So that means that learning with long windows is expensive. But for memory traces with a forgetting factor less than 1/2, we showed that any two histories will be mapped to two different points in space, which means that there is no compression happening, and actually memory traces remember everything. So this means that the complexity of this function class is infinite, and learning is completely intractable. But we also saw that to actually differentiate two histories that differ only far in the past, we need to zoom in a lot into this space. And we can limit the resolution of a function class by constraining the Lipschitz constant. So this is what we do in this work. We consider this function class that is the same as before, but now with a constrained Lipschitz constant. And for this class, we can again derive upper bounds on the metric entropy. These bounds on the metric entropy allow us to compare the efficiency of learning with two different function classes. So specifically, if two function classes both attain the same minimum return error, but one of the classes has a lower metric entropy than the other, then we can say that learning is more efficient with this function class. And this brings us to our main results. Our first result shows that learning with windows is not more efficient than learning with memory traces. Specifically, no matter what the environment is, for any window length m, we can always construct a forgetting factor lambda and a Lipschitz constant L such that the corresponding memory trace function class attains the same minimum return error and has the same metric entropy as the corresponding window class. However, for small lambda, we can actually show something similar in the other direction. So if lambda is less than 1/2, we can show that learning with memory traces seems not more efficient than learning with windows. So given a Lipschitz constant L and a forgetting factor lambda that is less than 1/2, we can construct a window length M such that the return error achieved with both function classes is comparable, and the metric entropy of the windows scales according to our upper bound on the metric entropy of memory traces. However, this result only holds if lambda is less than 1/2. If the forgetting factor is greater than 1/2, then we can show that there are environments where learning with memory traces is significantly more efficient than learning with windows. And specifically, the T-maze example from earlier provides such a case. So here, to accurately represent the value function, the metric entropy of windows needs to scale exponentially in the corridor length, while the metric entropy of memory traces scales only polynomially in the corridor length. So to summarize, we can show that with lambda less than 1/2, learning with windows and memory traces seems equivalent, while learning with lambda greater than 1/2, there are environments where traces are much more efficient. There are no environments where windows are more efficient than memory traces. So why can memory traces be more efficient? So one case is like the T-maze, where most of the possible histories of observations are not relevant. And this allows us to use a small Lipschitz constant L combined with a large lambda. However, there are also other environments where the exponential moving averaging behavior of memory traces is actually useful. So for example, in this hidden Markov model shown on the right, where there are two states and a probability P of transitioning and a probability Q of getting a wrong observation. If the probability P is small, so we are likely to stay in the same state for a long time, and the probability Q is large, so we are likely to get a wrong observation, then it makes sense to average over a long history of observations. So we want a large lambda, and this is exactly what we see in this case. Now finally, we also did some experiments with PPO and with TD learning to see if memory traces are useful in practice and if they can be used as an alternative to frame stacking. And we see that in many cases, memory traces do significantly outperform frame stacking. And that's it from me. Thank you very much for listening.